Hey everyone, my name is Seth. Some of you might know me as Tulu from my Utility AI tutorial series on YouTube. And my obsession with game AI started a couple years ago when I was simply trying to make an NPC that would just go farm resources and then go drop them off at some storage unit. And I went through all the typical beginner stages of game AI development. I first tried to script my own AI code that ended up turning into spaghetti. I bought a bunch of find a state machine and behavior tree systems off of the asset store without really understanding how they worked. And I kept getting the same result every time. Just, an NPC that looked really stupid and robotic going back and forth between hard-coded positions. So it wasn't really hitting the itch I had, which was to somehow get the NPC to think and act for itself without me having to write code to handle every situation. So if that sounds similar to what you've gone through or what you're currently going through and you're not sure how to proceed, then this talk will hopefully get you out of that rut. I'm going to show you a modular and extensible architectural approach that can support advanced AI frameworks like utility-based AI systems, planning systems, deep learning models, and any other fancy frameworks you can think of. This won't be a talk about how to build those frameworks, just because that's out of scope for a short 25-minute talk, but it will be about how to design an AI agent and then how to build a singular modular code base that you can then take those more advanced AI frameworks and plug it into that code base to power your NPCs. It's just one approach that might not suit everyone's needs, but for those of you who want NPCs who can think through and solve problems on their own in the game world, it'll be very helpful to get you started in the right direction. So with that, let's start with the high-level overview of what is required for an intelligent agent in a game. So at the highest level, an intelligent agent needs to be capable of taking some sort of game world data and then performing some sort of logic on that data and then outputting some sort of optimal action or optimal sequence of actions, which we'll call behavior. That's the most basic operation that an intelligent agent should be capable of doing. Now, let's take this and go one level deeper to flesh this out more. So now we're taking our black box logic module here and splitting it up into three different modules. We have the sensor module, the decision maker, and the actuator. And the sensor is responsible for basically detecting the game world data that's sitting in your game scene. It's transforming it into some sort of structured data and then feeding it into the decision maker. And then the decision maker will run its processing logic on that structured data and then decide based on that data what the optimal behavior should be. And then we take that optimal behavior and we feed it to the actuator, which is then responsible for executing that behavior and making the agent do what it's supposed to be doing. So at the bare minimum, an intelligent agent needs these three different modules. And this approach here is nothing new. It's called an agent-based model. And this has been around since the 1950s when people first started trying to program AI into computers. So now if we take this agent-based approach and break it down even further, then we actually start seeing a very interesting design pattern arise. So now we've taken the sensor module and broken it up into individual sensors, for example, the visual sensor, the audio sensors, and any other sensors that your agent might require to gather game world data. The decision maker is still a little black box of its own, but we'll talk about that more. If you want to be really fancy, you can actually throw in some sort of memory module here where it actually stores the information that is detected by the sensors so that the agent has basically a memory of data about the game world. And then these sensors just periodically have to update this memory module, and the decision maker will have access to both the memory and the visual sensors to get data to make decisions. And this is kind of where the idea of blackboards come in. A blackboard is just a particular implementation of what can be called a memory module. It's a general container of knowledge that is updated over time by the sensors, and the agent just has access to that blackboard to make decisions off of. So back to the decision maker. The decision maker takes in the structured data and then outputs an optimal behavior. And then it passes it into the actuator module, which can actually consist of multiple different things, because basically the actuator, as we mentioned before, is just responsible for taking the behavior and making it happen. And that can happen with through a coordination of all these different types of logic that's going on here. At the very least, you're going to probably need some sort of action runner that handles talking with the rest of the logic that sits on your agent. For example, the action runner might based on the optimal behavior it got, it'll reach out to the movement logic and tell to move the agent to the target where the action is supposed to happen. Or if the agent has animations to play, the action runner will play the appropriate animations for the action that's currently running. So the sensor and the actuators sit in between your game world mechanics and the decision maker. They kind of like serve as the interface between the decision maker and your game world mechanics. And your game world mechanics don't change, right? It's once you code it there, the logic there is going to be the same. For example, if there is a method to open a door, that open door method will always run the same logic, and the action runner can access that open door logic method and run it. And that's so the logic to contact the scripts that contain the open door method, that logic is going to be the same every time. Same thing with the visual the sensor modules. These guys are the logic here. If it's looking at something in the game world, the logic to do that lookup of information is going to be the same every time. So the code in your sensors, once you code it and put it in place, and the actuators, once you code it and put it in place, these don't change. What you do have the freedom to change is actually the decision maker. Because you have abstracted the decision maker away from your game world mechanics, it sits here and all it needs to be able to do is to process the structured data and output an optimal behavior. So you can really plug in any decision-making system here. You can plug in a utility AI system here. You could plug in a planning system here. If you want to, you can even train a large language model that takes in structured data and outputs in a sequence of actions. And you could plug it into this decision maker here. You could train a reinforcement learning agent that takes in this data and then outputs a set of actions, and it could go here. So this agent-based approach provides a very modular and extensible way to code an agent for emergent AI systems, because you have the freedom to just plug whatever you want into this decision maker. So now that I've shown you an abstract way of thinking about the general intelligent agent and its necessary components, let's go ahead and jump into Unity and see an example of this in action. So this is just a very simple village setup that I have created here, where there's a couple different things for these little purple agents to do in the village. Here, this great thing here is the forge, where the agents can come and craft something. They have these mines over here that they can come mine, and there's some trees over here that they can come chop. And then there's a fair area here where the agents can come and chill out at. And so those are a few things that the agents can do. These white little spheres here are critters. They're just little critters in the village, and they're just randomly wandering around. And their purpose is to just kind of scare off the agents. So, and the point of this is to show that the agents, even though it's carrying out an action, or if it already has decided on a behavior, if the agents come close enough, they can sense these little critters and then immediately change their plans or action to react to these critters. And for this simple simulation here, the agent will just immediately start fleeing. They'll just drop the plan or action they're doing, and they'll just flee. So let's take a look at what's actually sitting on the agent here. So you can see here, I have followed the agent-based model that we were discussing earlier. We have a sensor script, and then we have we have two different decision makers modules here that we can pick from. and then we have the action runner and the behavior runner. These kind of make up the actuator modules. I decided to split them up into action runner and behavior runner because it was easier to handle sequences of actions with these two running side by side. And we just have a couple different support scripts here. The AI mover, which is responsible for navigating around the nav mesh for the agent, and then the action progress tracker here that's just responsible for tracking the progress of the action if the action runs over a certain amount of time. And then this AI agent script here is just kind of just the script that holds a list of references to all the other important mono behaviors. So we can pass or inject this AI agent script to other things that need access to all the other scripts that are sitting on the agent. So I want to turn the attention to these two decision maker scripts here. One is called random multi-action decision maker, and one is called random single action decision maker. And the point of having a multi-action and a single action is to kind of emulate the different decision maker algorithms out there. So for example, if you're running a planning system, then planning systems typically output a sequence of action, which are multiple actions chained together. And so this random multi-action decision maker, even though it's just randomly chaining actions that it picks from this list, the point of it is that it emulates some sort of planning system that outputs a sequence of actions. Whereas this decision maker here, where it just picks a single action from this list here, it's meant to emulate decision-making algorithms that pick the next action for the agent to do. So for example, utility-based AI systems. So if we're going to run a single action decision maker, we'll turn this on and drop it here. If we want to emulate a planning system, then we just grab this here and drop it here. And that's the beauty of this system, is that because, as I mentioned before, because we've abstracted the decision maker logic away from the mechanics of your game world, we can drop in any algorithm in here. So let's actually go ahead and run the simulation really quick to see this stuff in action here. So again, we're starting out with the single action decision maker. And so you can see the single action decision maker picks out the next action and then hands it off to the action runner or the actuator modules, and then the behavior runner and the action runner are both responsible for making that action happen. So he's mining ore right now, and then he's wandering, and then he's going to attend the fair, and this is just going to keep going on and on and on. And let's see if he runs into this little critter here. There you go. You see that he ran into the critter and he got scared, so he immediately changed his action and he fled. There you go, and you can see the other agent here also doing the same thing. And again, like I said, this single action decision maker, it's just randomly picking an action from the list, but it's meant to emulate systems like utility AI systems, where it's just picking the next best action and not looking any further than that. So let's go ahead and switch this over to the multi-action decision maker, which is meant to emulate like planning systems. I just come here, turn this off, turn this on, and drop it into the AI agent. And if we press play, we should see a plan get generated. There you go. The agent quickly generated a plan or a sequence of actions, and now it's just proceeding to execute that plan. Okay, let's see if it runs away from the critter. Okay, there you go. You see that he got close to the critter, so he dropped the plan he was going to execute, and he generated a new plan to follow. So let's now jump over to the decision makers. As I mentioned before, we have a multi-action decision maker and a single action decision maker. And the point of these two is not to implement any fancy logic, but rather just to emulate systems that either output a single action or output a sequence of action. So we see that both of these decision makers actually inherit from a parent class, the decision makers. So let's go take a look at the parent class. It's just an abstract class that has a reference to the behavior runner, and then it has an initialization method, and the key method here is the decide behavior. It's an abstract behavior, so any class that inherits from the decision maker just needs to implement the decide behavior. So if we go to the multi-action decision maker, we see that we implemented the decide behavior method here in this way, where our algorithm is randomly generate a plan. And in this method here, then we just randomly piece together a certain number of available actions, and then load that sequence into the behavior runner via this method here, load plan. And the same thing happens in the single action decision maker also. We override this decide behavior here, but now we implement a different logic, different decision-making logic here, where it's just selects a random action from the available list of available actions, and then it loads that single action into the behavior runner. So both of these inherit from decision maker. They implement decide behavior in a slightly different way. So that demonstrates the modularity of this agent-based model approach, where you can, as long as you implement the decide behavior, you can code whatever logic you need to code in here. So if you want to plug in a GOP system in here, you want to plug in a utility AI system in here, you can. It just needs to happen in this decide behavior method here. So now let's jump over to the behavior runner, because that is what actually takes in the action or sequence of actions from the decision maker. If we follow this load plan here, we can see that the plan gets stored, and then the start behavior gets called. And in the start behavior, the action runner is actually just being loaded with a single action. So the behavior runner has a reference to the action runner, and whenever the start behavior method gets called, in this case, it just dequeues a single action into the action runner. So now we can go ahead and trace that to the action runner, and we see that the action runner has a reference to the current action here. And when the behavior runner calls this load action, the action runner just goes ahead and loads the current action, and then it initializes the current action by injecting the agent into it, so that the current action has access to all the information it needs to run its logic. Now, if we look up here, the action runner is actually listening to the AI mover here, specifically this event on reach target. So every time the AI mover moves the agent to the target of the action, then it raises this event here, which then causes the action runner to run the start action method. And this is actually what jumpstarts the running of the action. We can see here that the current action, start action, is called, injects the agent into it for information, and then it sets this is running bool to true. And then in the update method of the action runner, since the boolean is now true, the current action can now start updating itself. And so this is useful if you're running actions that take time and need to happen over multiple frames. If any logic that is sitting in the update action, then that gets run. So by breaking up the agent into these three different modules, the sensor, the decision maker, and the actuators, we've implemented a very modular and extensible AI system where all you need to do is customize the logic of the decision maker. So you can plug in a GOP system, a utility AI system, a large language model, a reinforcement learning agent model in here, and it will still run the same way because all that this decision maker module does is it takes in data from the sensors and outputs a sequence of action that gets fed into the action runner and the behavior runners. All right, now that we have an agent-based system in place where we can plug into it whatever AI framework we want, let's talk about what framework you should use for your game. This is a very common question I get all the time, and I often see people trying to force their game to use frameworks that just don't work well with the type of game that they're building. So hopefully this will give you some guidance. But first, caveat. This is just a general guide to help you understand what frameworks are available and generally where they're used. More often than not, you're going to find yourself combining bits and pieces of different frameworks together to get the NPC behaviors that you need for your specific game. So look at this diagram as a general guide on what each framework provides in comparison to all the other frameworks. So with that, let's go through them. On the left, we have what I call if-then-else frameworks, and these include decision trees, finite state machines, and behavior trees. Under the hood, they all run very similar logic in terms of picking an action to run. They simply check to see if a set of actions are fulfilled, and if yes, then they just run that particular action. This leads to them being very easy to understand, implement, and gives you tight control over what actions are performed by the NPC. Their downfall, however, is that as your game grows in complexity and you need to add in more actions and behaviors, you end up having a massive intertwined set of conditions to check for, and it just becomes a nightmare to manage. And the reason for naturally having so many conditions to check through is because you basically have to hard code condition checks for every type of situation the NPC will run into. So the more actions you throw in there, the more conditions you will need to check in your web of actions. But these are only problems that you run into if your game is too complex and it has a lot of actions that the NPC needs to be able to do. If your game is small and the AI needs to be simple and predictable, then these if-then-else AI frameworks actually work perfectly fine. You don't need anything more advanced. Okay. Now let's take a look at the center. In the center, we have what is called algorithmic action space exploration frameworks, which include things like utility AI, hierarchical task networks, and GOAP. Now, instead of hard coding conditions that check for running every action under every situation, you instead write algorithms that filter through the actions available to the NPC via some sort of scoring or prioritization metric. Whichever action has the most optimal score or priority then gets run. Now, since the algorithm to filter through the actions is the same for every situation, this gives you the freedom to just define all the actions you need to include in your game without having to worry about, having to hard code what exactly the NPC should be doing for this situation and that situation, and that, in this situation, it needs to be doing this specific action. The decision-making algorithm handles all of that. So that's why these AI frameworks are much more scalable to handle large, complex games. It can also give rise to unexpected NPC behaviors that end up driving emergent gameplay for the player, which can give the game a lot of replayability value. The drawbacks, however, are that these systems are usually hard to understand, hard to implement, and hard to tune. On top of that, if you run these decision-making algorithms on every NPC, that can become very expensive if you have a lot of NPCs. All right. Now on the right, we move towards what I call learning agents, which is actually really an entire disciplines of their own and not really, quote unquote frameworks in the same sense of the previous two categories. Learning agents, whether they be evolutionary algorithms or machine learning agents, basically explore the mechanics of your game world and then develop an understanding of how to operate in the game world. So after enough training in your game world environment, these agents will be able to do literally anything they want, which is pretty darn cool. Instead of having to design and code entire complicated code bases to algorithmically choose actions, we just focus on training these agents in your game world. And the models themselves will then generate behaviors from a black box which contains their internal understanding of the game world. Obviously, this then gives rise to truly unscripted emergent NPC behaviors and is scalable in the sense that you don't have to write all these decision-making algorithms anymore. It's learned into the agent's understanding of the world, and the agent will do the rest. You just need to train these learning agents, and the training becomes the main bottleneck of this approach now. Training learning agents generally take a lot of time, a lot of data, and a lot of computing power. On top of that, the agents can only function in the specific environment of the game that they were trained on. That means that if you make any modifications to your game mechanics after the training for any reason, then the learning agents will most likely have to be retrained again to some degree. But if you can somehow overcome all these limitations, then you'll probably have the most autonomous NPCs for your game. So these are the general categories of AI frameworks that are available for game AI, and you just have to pick and choose which ones best fit for your game. Pick and choose the different parts of each framework and mix and match them so that you achieve the behaviors you want. Okay, so I hope this talk has helped you develop more intuition about how to build code around AI frameworks and which frameworks you should use for your game. There are so many more details involved in the process of implementing game AI. For example, how do you represent and work with world states? How do you coordinate AI with animations and other systems in your game? How do you interrupt an NPC's current behavior? How often should you run the AI decision-making process? And how do you optimize everything? The list is endless. So if you're working on a game and looking for more expertise on this stuff, I just started my game dev studio, and we focus on making AI-driven games and provide hired consulting on this area of game dev. So feel free to reach out to me at any of these channels of communications I have listed here, and I would be more than happy to talk game AI with you. I've also listed some great books here that I personally study a lot for game AI, so I highly recommend these books if you're interested in diving deeper into the topic. That's it for me now. Thank you so much for your time, and I will see you on the other side.